Good morning, class. Today is October the 7th, and so today is the video for October the 8th. And so today we're going to start talking about solar power, solar energy. And up till now, we've talked about stored energy on Earth, which can be chemical or can be nuclear, and we've covered those things. And so today we're going to start talking about solar energy, which is it's perhaps a useful analogy, but not necessarily very instructive, more philosophical than anything else. That the stored energy on Earth, to a certain extent, whether it's uranium or oil, kind of represents the mankind's inheritance, so to speak. That as we became civilized, we found all these sources of energy that we could convert or burn however we want to create useful energy from. Whereas solar energy is kind of what we earn on a daily basis. And so we're going to get started by understanding how much that is. And if you have the sun, and we went through in the introduction that the sun is outputting light, electromagnetic radiation, to the tune of 4 times 10 to the 26 watts. And so here we are at Earth. And so if you call this our orbit, that 4 times 10 to the 26 watts is radiating equally in all directions. And so at the surface of the Earth, the power per unit area, remember we use P for that, is 4 times 10 to the 26 over the surface area of that sphere at our orbital position, 4 pi r orbit squared. And if you plug in the numbers, you get 1400 watts per square meter. So up in space, now we went through how down on Earth that becomes lower. It's 1,000 on a very clear day, but up in space, so to speak, there's 1400 watts per square meter hitting the Earth. And so if you take that and you multiply it times the cross-sectional area of the Earth, that's it, just treating the Earth as a circle, then basically the amount of solar energy incident is equal to 1400 times the area of that circle. I mean, the Earth is presenting itself as a disk, basically. Pi, and I used r radius for the radius of the Earth, squared. Pi r squared, the area of that circle. And that works out to, okay, I'll write it out first this way, 1.8 times 10 to the 17 watts. Now, here I'm going to introduce a quantity called a terawatt, which I might have slipped in here and there. A terawatt is 10 to the 12 watts. Now, we went through how 1 quad per year is 33 gigawatts. All right, so that's equal to, okay, well, let's go through. So 100 quads per year, which is roughly the energy consumption or the power consumption of the US, is equal to 3,300 gigawatts. So that's equal to 3.3 terawatts. So a terawatt is kind of a useful large amount of power because the US, for example, uses 3.3 terawatts at 100 quads per year. And so it's sort of a useful frame of reference. So if I convert that to terawatts, that's 180,000 terawatts. So it's a lot compared to what we consume, 3.3. Now, of that amount, some is reflected. The reflectance, I'll write little r, of the Earth is 37%. So what is kept by the Earth? Earth kept. You take 1 minus 0.37, and that works out to 110,000 terawatts. So of that 180,000 terawatts, 70,000 is reflected back into space. Now, this number 37%, the reflectivity of the Earth, is sometimes an interesting thing to think about because, I mean, you can imagine some parts of Earth are more reflective than others, particularly our ice-covered areas. And so, as global warming is occurring and ice is melting, that number is getting smaller. So that's a secondary factor for increased warmth of the Earth because obviously if that just drops by a few percent, then that number goes up quite a bit. So, you know, that's just sort of an interesting aside there. But let's go on with, you know, what's happening on the Earth. So let's draw the Earth bigger. And let's draw the Earth's atmosphere. Now, the Earth's atmosphere isn't that thick. But I'm using it for illustration purposes here. So, so to speak, I mean, this is kind of the hard part of the Earth. And that little envelope is our atmosphere. All right, and so basically, we have, if you subtract off the 37% that's reflected, we have 110,000 terawatts of solar energy incident or captured by the Earth continuously. And of that amount, of that amount, 20% of that is absorbed in the atmosphere. And so what reaches the Earth then, so basically that's somewhere around 20,000 terawatts, just using rough numbers. And so what is incident upon the Earth's surface is 90,000 terawatts. Now, so you know, in a sense, that represents how much solar power on a continuous basis is, in principle, the ultimate amount accessible by the Earth. If somehow you could convert all of that into useful power. But of course we can't. But you know, we're trying to get a frame of reference here of what these numbers are. Now, there has to be always something called energy balance in any system. And so if we have, you know, continuously 90,000 terawatts incident on the Earth's surface, well, that's, you know, that has to be balanced in some way. And how that's balanced is through infrared radiation. Now, in the notes I discussed black body radiation. I know most of you haven't had any modern physics, but basically I think you understand that, for example, I am radiating infrared energy. You're familiar with the concept of thermal cameras, and you know that any warm body radiates a certain amount of power. And so the Earth does so as well, all right? And that amount of infrared radiation, all right, if you work out the numbers, is equal to 180,000 terawatts. And it is proportional to T to the fourth. Of course, T is in Kelvin here. So, at the Earth's average temperature, which, what did I use there? The Earth's average temperature, 13 centigrade. T average is equal to 13 centigrade, which is 286 Kelvin. Okay, at the Earth's average temperature, it is emitting infrared radiation of about 180,000 terawatts continuously. And so what's going on here? Well, the difference between 90,000 and 180,000, or 90,000 of the IR is absorbed in the atmosphere. And then the planet is in energy balance. Because we have 90,000 terawatts incident upon the Earth's surface, oh, I'm sorry, the other way around, 70,000. So, the IR into space is equal to 180,000 minus 70,000, 110,000 terawatts. And that matches the 110,000 that is incident upon the Earth as solar radiation. So if you did an envelope around the Earth outside of the atmosphere, there would be 110,000 terawatts of solar power continuously incident upon our planet, mainly in the visible, okay, but it doesn't matter, that's the amount of power it is. And the Earth, if you look with an IR camera, would be emitting emitting, if you looked out in space here, 110,000, and so those equal to each other, and the planet is in balance. And it relies upon this absorption of 70,000 of that IR energy in the Earth's atmosphere. Now, how does that occur? Well, that occurs because of polar molecules in the atmosphere, particularly water vapor, but also carbon dioxide and methane to a certain extent. And so that number goes up as we produce more CO2 in the atmosphere. And so basically, say it was that number in the year 2000 and the year 2050, okay, I mean, I'm just making up numbers here, that could be 75,000. And so then that would drop to 105. All right, think about it. Okay, if because of increased CO2 in the atmosphere, that went up to 75,000, then that would drop to 105 and we would no longer be in balance. Well, what would happen? Well, this would have to go up, meaning that would have to go up, the temperature of the Earth. And that's exactly what's happening. The temperature of the Earth is going up to keep the entire system in balance through increased infrared radiation from the surface. And that is, solar energy on a sort of global basis on the Earth, and how it gets distributed. So as far as what I want you to understand, okay, I do want you to understand or be cognizant with, you know, the fact that this is 1400 watts per square meter here in space, things like that, and be able to do certain calculations. And I do want you to understand that the infrared radiation of the Earth's surface goes as T to the fourth. And, you know, I know it's a little complicated, but be able to walk through these numbers a little bit. And maybe that might be a good homework problem. Okay, so that's all okay and everything, and we understand of all this radiation that's incident and everything else going on, what's happening. Well, so let's start talking about wind. Now, this is on solar energy, and so, you know, I mean, you might think we should start with solar panels, and we will get to solar panels, but since we're having this discussion about the total amount of power incident on the Earth, let's talk about wind and the amount of power. I'll put it this way: absorbed in the atmosphere on a continuous basis. All right, what is it equal to? It's equal to 70,000. That's the IR component from the Earth, plus 20,000, roughly, which is the solar power absorbed in the atmosphere. So we are equal to 90,000 terawatts absorbed in the atmosphere on a continuous basis. And that's what gives rise to, you know, wind and things like that. I mean, now that 90,000 cannot be considered, you know, the availability of wind energy. We're going to try and construct that now, but it sort of gives you an idea or a reference frame that on a continuous basis, 90,000 terawatts of power is being absorbed by our Earth's atmosphere. All right, and then what happens? Well, okay, to think about what happens, maybe we can use our little diagram of the Earth over here. Let's make some room here in our atmosphere. All right, so we got all this power being dumped in the Earth's atmosphere, and of course the majority of it is, I erased the sun over here, but the majority of it is at the equator. And so what happens now, let's first imagine if the Earth was not spinning. If the Earth was not spinning, because it's hotter at the atmosphere and colder at the poles, you would have a natural sort of cycle of wind like this. Okay, and I could draw the other four quadrants here, or so to speak. But basically, air would tend to rise. Our air would tend to rise near the equator and flow north along the outer atmosphere, and then fall at the poles and flow south then near the Earth's surface. And so if the Earth were not rotating, the wind would always go south, at least in the northern hemisphere. In the southern hemisphere, it would always go north. But the Earth does rotate, okay? And what happens then is kind of complicated, because basically that rotation leads to various shear forces on the wind that truncate this there. That air doesn't make it all the way to the poles because of the rotation of the Earth. It's kind of sheared away and it falls there. Now, what happens next is that the air is kind of like gears in a mechanical system that has to go in the same direction. And so you get a cell like that. And sort of naturally, all right, it has to, I can't draw arrows here. Sort of naturally, it has to form 3 cells roughly. One near the equator where the air still rises, and then instead of making it all the way, it tends to flow down or like that. Okay, and then this turns into via rotation, basically air in that direction. And so if you think about the Earth, the way I've drawn it here, well, there's only one way to draw it, North Pole. That air always flows from east to west. And so you call that easterly wind because you always talk about what direction the wind comes from. And then this cell here results in air flowing that way. And so like here in the United States, if you ever notice, weather tends to come from the west to the east. Okay, roughly. And then over here again, near the poles, it doesn't really do much of that because you're up by the pole. It tends to go in a circle around the pole. And there's a picture in the book that are in the notes that goes through this. And so you can sort of understand why the wind tends to go roughly in the direction it does most of the time. And there's I'll just maybe sort of show this. There's this picture in the notes showing what the rough wind speed is, and this is for 50 meters above the Earth's surface. And what you can see is that over the oceans, it's roughly around 7 to 8 meters per second. This is wind speed. And over land, it kind of averages, much smaller, maybe 2 to 5. All right, and why is that? Well, it's because land blocks the wind, and so the wind is slower over the continents. And so what happens? Well, okay, here on the coast, on the coastlines, it's kind of in the middle like that, and so we would like to put windmills near the coast to capture that high wind speed of the oceans. One interesting thing is if you notice, I'll put up the diagram again. This band right here, that's because south of South America, there's basically enough room there that there's no obstructions all the way around the Earth, and so this bottom cycle here, which is this easterly, basically forms a circle, and the wind speed there, averages above 9 meters per second. It's very fast. All right. Now, how do we capture wind? Well, with windmills, and there's various types of windmills, but usually, okay, all right, ideally, right, you would have land, and you'd be near the ocean, and for example, the Lewis windmill, right, captures that wind that tends to come off the ocean continuously. And you know how to do this calculation. You basically, the wind power incident, you take the area subtended by the blades times 1/2 rho v cubed. And so you know how to do that now. That's the power and the wind incident, and the efficiency of a windmill tends to be around, say, 30%. Meaning you take that and you multiply it times 0.3, and that gives you the amount of power that you're going to get out of your windmill on an average basis. And so of course it goes as V cubed, and you want to put your windmill in a windy spot. Windy spots, as indicated here, are near the ocean, as well as on the tops of ridges of mountains and things like that. And so I'm not going to put up the chart of electric power versus year of our country, but remember, wind has been steadily rising, is up around 35 terawatts now. Okay, so what we would like to understand, one of the things we would like to understand, and well, actually, you know, your final project. So today, in the year 2019, electricity from wind is about 35 gigawatts. And the question is, okay, 2050, what? And that question has several ways of answering it. Which one way is you can just think, okay, how many more windmills can I put up? And you know, you go from there. And people have done that, and they've made estimates. And they've made estimates that, well, for the world as a whole, put up more windmills. And basically, they've just calculated that 72 terawatts is possible. And you know, that sounds okay. So that's 7,200 gigawatts. The indication from that now the U.S. is only 6% of the landmass of the world. I think that's right. So based upon that, 72,000 gigawatts, all right, times 0.06 would indicate that U.S. Possible is, okay, now remember what we did here, 72,000, that's 72,000 gigawatts, right? Because a terawatt is 1,000, or a gigawatt is a terawatt is 1,000 gigawatts. And so if you take that times the U.S. percentage of the landmass, 0.06, you get 4,300 gigawatts. Potential, according to that. Now, I don't think that you should put down 4,000 gigawatts for wind power, and there's a variety of reasons for that. One is that this number it seems high, and so what I did in the notes was I took sort of, you know, an average wind speed of 5 meters per second over land, and what I did, you know, this is sort of a different calculation, is to take the energy in the wind, all right, as 1/2 mv squared, and summing it, and basically within what did I do? 80 meters height, and I came up with 4 times 10 to the 17 joules. And then I said, well, you can take that and you can divide that by, so power is energy per unit time, and so let's divide that by 24 4 hours times 3600, 0.2. So that's saying that on a continuous basis, I'm going to extract 20% of that energy. So every day I extract 20% of that energy, and that only gives me 1 terawatt. All right, so that's a lot lower. The answer is probably somewhere in the middle, and so my guess is that you know, this number is actually so if we take let's say 10 terawatts, okay, somewhere between 1 and 72, and multiply it times 0.6, then if we use that number, I should be able to do this in my head, 10,000 times 0.6, 0.06. 600. Okay, so what I just sort of roughly, very roughly calculated for you was that right now, 35 gigawatts, in principle, probably that number can be as high as 600. If we really worked hard putting windmills up everywhere and capturing, you know, as much of the wind as we could. So now, is that what you're going to put down in your final project? Well, be careful. All right. Okay, so first of all, right now in the year, you know, W total, it's 2050. A lot of subscripts here. Total, the total electric power in the U.S. in the year 2019, we just went through, is 454 gigawatts. Okay, so I mean, it's saying we could get all of our electric power from wind. In principle. Now, why wouldn't we be able to do that? Well, there's not so much in the notes on this, but the reason why is because that is variable. The wind doesn't blow all the time. All right, so how do we solve that problem? Well, there's kind of two steps. The first is the smart grid. Now the smart grid, there's a whole course on this, and I encourage you to take it. We're not going to be able to do a whole course in it. I'm just going to describe in a few minutes here what it's about. What the smart grid is doing. Let's say wind goes down. All right, and you're getting, let's say you're getting most of your electricity from that. Well, what do you want to do? You want to make the demand go down. All right, so so the smart grid is the idea that we will evolve a whole set of mechanisms that we can alter the demand going out there, and it's based on the fact that the current grid has approximately 0 storage. There is little bits of storage here and there, but if you you know, compare the numbers that you need to compare with the numbers you have, it's approximately 0. Meaning, when the utilities generate electricity, all right, the idea is that every amount that they generate minus the losses in the distribution are going to get used out there by someone. And so what the smart grid is saying is, okay, we can have demand response. Now, this currently exists in sort of clunky fashions. One simple mechanism is that utilities go to large consumers of electricity, for example, large factories, and they say to them, we will lower your overall electric rate a little bit if you agree that, for example, currently on very hot sunny days in the summer, when everyone's got their air conditioner runs on and you run out of capacity, they say, okay, on those days, we may call you up and say you have to shut down parts of your factory in order to get that lower rate. And so and that exists, and it works very well. And I know a lot of large factories that utilize this service. And so basically, it's the control system. It's very simple. It's done through a phone call. So it's very clunky and mechanical, but it works very well. And of the companies I know, they get that phone call once every couple of years. So it's a good deal for them. It's a good deal for the utility because they can keep supplying everyone with the electricity they need without having to overbuild their capacity. And so basically, the smart grid is the idea that we will evolve that ever further to the consumer level, to the point where you may have an app on your phone where, okay, let's say we'll talk about, let's say the wind stops blowing and we're getting a lot of our power from wind in a particular area. So as a function of the wind speed, the rate of you pay for electricity, how much you pay per kilowatt hour, would be dynamic, sort of going up and down with the wind speed, or the other way around, going up as the wind speed goes down and vice versa. And so you might have on your phone a little app that says, okay, this is what you're paying for electricity right now at this very moment in time. And you may look all of a sudden and go, uh-oh, 25 cents, I don't want to pay that. And you go and you turn off the oven or the dishwasher or something. So there's various ways to try and do this. Now, when might we have to do that? So right now, okay, we haven't talked about solar yet, but in the year 2019, wind was 35 gigawatts, and solar, I didn't print that page. Solar, I think, was around 15. So these are rough numbers. So total, around 50, wind and solar. And so, of course, solar is variable as well. In other words, it's intermittent. And so right now, in the year 2019, wind plus solar is somewhere around 50 or 450 or 1/9, whatever that works out to be, somewhere around 12%, I think, of U.S. electricity. And let me check that number here. Yeah, maybe 11%, somewhere around 11 or 12. So right now in the year 2019, there's roughly no smart grid in place. I mean, very little. There's and so we're working fine at around 12. And the idea is that this would be required when W wind plus solar exceeds around 20 to 25%. Because there's various tricks you can play ahead of time. You can have variable capacity plants and things like that. But certainly right around 25%, you're going to need more sophisticated demand response and other types of smart grid, including smart grid response systems that are automatic. Things like, I mean, the ultimate smart grid is, there used to be things called brownouts, where when the utility was not able to supply all the electricity you needed, they simply turned down the voltage. They don't do that anymore, but there can be more sophisticated versions of that where they can sort of send out signals and turn down your lights and things like that. So, 25% or so is when you have to start doing these things. Now, how long would it work? Because the next step is storage, which is primarily batteries. Right now, as I mentioned, there's very little storage in the electrical distribution system, and so you get the idea that if we had substantial storage, it would be a lot of batteries. Now, there's various proposals for how to do this, and fortunately, battery technology is developing rapidly for vehicles, and the same battery technology can be used to store power, to store solar and stuff when the sun's shining and the wind's blowing. Now, this probably would have to occur certainly above 40%. So if you look at the timeline here, okay, in the year 2019, okay, 12% wind plus solar. All right, and that's rising pretty rapidly, and there's a chart in the notes that indicates that by 2025 that may be 20%, and let's say 25%, and so we would start to have the smart grid. And that would work up till some year where it's 35, maybe 40%, maybe. And then beyond that, batteries or storage. Now, storage leads to a whole set of problems, and the number one is cost. It costs a lot to, batteries cost a lot, and they don't last forever. We may have time to circle back and talk about battery technology and address, this issue. There are some people that think that this is perfectly possible to have large-scale storage to store up wind and solar when that's happening, and so you can use it when it's not. There are some people that think it's not possible. All right, so kind of right now, okay, the non-storage limit of wind plus solar, well, it depends. I mean, let's say it's 500 gigawatts in the year 2050, just to have a number. It's around 200. So you can see that the limitation is not how much wind there is. The limitation is whether you start to institute storage. So your final project, I mean, to a certain extent, is kind of easy. You can basically, say, okay, I will simply limit wind plus to around 20 to 25% because that's possible with the smart grid. Or if you want to have more, then you have to start talking about storage, and you have to come up with good arguments as to why that's possible. All right, so let's move on to solar itself. And what we're going to do right now is, we're going to talk about the different forms of solar power. Because it's not all solar panels, and it's not even all solar panels on your neighbor's roof, but it's a variety of components, which I have a chart for in the notes, and I'll reproduce this here. So solar, all right, in this 2008 to 2020 has been roughly doing this. There's this smaller component, those are towers. So that's currently up to around 0.5 gigawatts. Now, a solar tower, there's a picture in the book. I'm not going to get into too much details because that's a relatively small component. But it's these sorts of things where you have a very large field of mirrors that focus the light up onto a generator in the tower, usually a steam generator. So now then there's a component, rooftop panels, and so that's currently up around 4 gigawatts. And then there's utility. So what are utilities? Well, those are these very large solar installations taking up, you know, I mean, almost nearly a square mile. And that's currently, you know, up to around 8 or so. And so basically, maybe 5, 9 today, and you get up to a total of around 20. And it's sort of interesting to look at this chart because it gives you a perspective of, you know, how much of solar is being driven by the homeowner and how much is being driven by utilities. And currently it's about 2 to 1 utilities, which is probably around what you would expect. So, you know, again, that's the year 2020 or 2019, and so in the year 2050, you're going to put a number down there, and you're going to keep in mind that, well, all right, if that number exceeds, you know, if the total wind plus solar exceeds 25%, you have to start talking about storage, and you have to make up good explanations for whether that's possible. All right, now what I finally want to leave you for, so basically, for the next lecture, for today's the 7th, so next week, so 8th, 9th, 10th, 11th, 12th. For the 10-12 lecture, we will learn about solar panels, technologies. So we're not gonna start talking about semiconductor physics right now, but we will do it. And the neat thing is that even if you don't like the idea of learning semiconductor physics, I can still teach you how these things work. But anyway, before that, you'll notice there's this chart here in the notes. And what that is the concept of solar insolation. It's not insulation, it's insolation. That basically refers to this, that for a given place, if this is time, all right, and this is P solar. Now remember, that can be up to 1,000 watts per meter squared. All right, it can't exceed that on the surface of the Earth. It's 1,000 on a very, very clear day. All right, and so what happens? Well, okay, at night it's clearly near 0, and then in the morning it goes up, and you know, maybe it does something like that, and You know, then there's a cloudy day, less cloudy day, you know, and so that's what solar power would look like over time. Now what insolation refers to is, okay, that is equal to 1,000. That is equal to every day. I'm trying to draw days here. Okay, you get the idea. Every day it goes up to 1,000 for a certain number of hours, which I mean, it's sort of the insolation hours, but I'll just call it T sub T or something like that. It's saying in this chart, if you look at the scale on the side here, that if you were to integrate this over time, because remember, energy is equal to the integral of power over time, that this energy would be equal to this energy. And so this makes calculating, for example, if you put up a solar panel and you want to know, well, how much electricity am I going to produce each year? Okay. This number for Delaware is roughly, and you can see there's a chart here that's color coded, of course it's more in the Southwest, is 4.75 hours. So if you put up a solar panel, all right, now that's for facing south and tilted, it's called at latitude. That basically means that you put up your solar panel, you faced it directly south and you tilted it so it was pointing up at whatever latitude you're at, which here is around 40 degrees. So that as the sun rose in the summer and went higher in the sky and lower in the sky, you got that best average. Basically, tilted at latitude means, okay, and you can figure out the geometry here, is that at the equinoxes, okay, September, March, the sun's rays are exactly perpendicular to the panel. And if you can't do that, if you lay flat, there's other charts for it. So you can use these charts to figure out, okay, for a given geometrical configuration of your panels, what the equivalent time the sun is shining at 100%, at 1,000 watts per meter squared. So this is a concept I want you to be able to have, and we're going to circle back to it after we learn how solar panels work and we start to calculate, okay, what can they produce. All right, so that's it for today, and we'll have our chat class in the morning.